Okay, in this last practice that we are going to perform in this recitation hour, we are going to deal with the estimation of relative performance, which is related to our last module of our course about output analysis. And in this question, we are considering the comparison of two system designs, which one is better than the other one. And in order to do that, we have run a few replications for each of the system designs in our simulation model. Okay, so the question says that suppose we are comparing performance of a queuing system under two different queuing disciplines based on the expected number of entities in the system. So there's a certain system for which we propose two alternative queue disciplines here. Okay, you can assume that in one of them we have a FIFO queue discipline, which is a first in first out system, and in the second system we can say that some of the clients are prioritized with respect to the other ones. Now we have run 8 simulation replications for both systems. It says 8 simulation replications, and we have used independent sampling. Please notice that we have used independent sampling, which means the random number streams used in all 16 replications were different. In the first replication here, we use a random number stream for examining the first queue discipline in order to generate the inter-arrival times or service times or whatever randomness that we need to introduce in our model. Now, when we are simulating the same system for the first replication under the second queue discipline, we are generating inter-arrival times, service times, and other randomnesses with different random number streams than we have used in the first simulating the first queue discipline. Okay, so this is an independent sampling procedure indicated by the question here. We definitely need to notice that because the procedure that we are going to follow is dependent on that. Okay, now we have 8 replications for the queue discipline, and in each replication the expected number of entities in the system are estimated differently, because in each replication we are also using different random number streams. And under the second queue discipline, we have such similar results, changing estimates for the expected number of entities in the system from replication to replication. Now, these values are the replication within replication averages. Okay, so these values in the row are within replication averages, and for these 8 replications, the sample mean is already calculated for the first queue discipline and the second queue discipline, and also the sample variance are also calculated for these 8 replication results. So this sample variance is the sample variance of these 8 values, and this sample variance is the sample variance of these 8 values. Okay, similarly, this sample mean is the sample mean of these 8 values, and this sample mean is the sample mean of these 8 values. Now, in part A, it asks us to build a 95% confidence interval for L1 minus L2, which is the difference between the expected number of entities in these two systems. Now, in a queuing system, if the expected number of entities in a system design is less than the expected number of entities in the second system design, then we can say that the first system is better, right? Because we do not want so much expected number of entities in a queuing system. Whether this is a queuing system in which the entities are human beings, I mean, imagine simply a banking system, the clients are going to be much more encouraged to enter the queue if the number of entities who are waiting system are less. So if you enter a bank which is so crowded, you definitely will be discouraged and leave that bank immediately, maybe you will renege from the system. Why? Because by observing that there are so many entities, so many clients in that bank, you can say that you are going to wait so much time until you get a service. Okay, so the expected number of entities, if this is less, then the system is better. Now, we are looking at the confidence interval between L1 and L2 here. Okay, L1 minus L2. Now, if L1 is less than L2, then this difference will definitely be negative. Okay, and we can say that we favor the first Q discipline in that case, because the first Q discipline produces a less expected number of clients in the system. And if L1 minus L2 is positive, then we would favor the second Q discipline. Okay. However, please remember that the simulation procedures, they always produce estimates for L1 and L2. Therefore, for this difference as well, we only have an estimation. And always we need to provide the estimations along with the confidence intervals that they have. Now, once we build a 95% confidence interval for the difference between the estimations, for the difference between the expected number of entities, if that confidence interval altogether with its lower bound and upper bound, if that confidence interval is in the negative part of the real numbers line, then we say that with a 95% confidence level, the first system is better, okay? Because with 95% confidence level, even the lower bound and the upper bound for this difference in the negative part, okay? However, when we built the 95% confidence interval for the difference between the expected number of entities, if that confidence interval is completely in the positive part of the real numbers, both the lower bound and the upper bound, then we should say that L2 is a better system, because L1, the first Q discipline with 95% confidence level, produces a larger number of expected number of entities. And finally, when we build this 95% confidence interval for the difference between the expected number of entities, if that confidence interval contains the zero value in it, in other words, if the lower bound of this confidence interval is in the negative part and the upper bound is in the positive part, then the confidence interval contains the zero value in it. If the confidence interval contains the zero value in it, we should say that the result is inconclusive. We cannot simply say, there is no statistical proof to say that one system is better with respect to the other one. All we can do at this point, if the confidence interval contains zero in it, all we can do is to increase the number of replications to get a much more solid result. And always increasing the number of intervals will always eventually will always remove zero from that confidence interval if the Q disciplines are effective in the performance metric, obviously. Okay, if the Q discipline choices that we apply is certainly affecting the expected number of entities in the systems, at some point when we increase the number of replications, we definitely get a conclusive result. Okay, now at this point we only have 8 replications which are independent in Q disciplines, in alternative Q discipline simulations. So we need to build a confidence interval, and the procedure requires to implement a confidence interval for the difference between L1 and L2. Now, in the first simulation, the statistical estimate for L1 is 10.0.188. And in the second Q discipline, the estimate for L2 is 10.0.963, which are basically denoted by y.1 bar and y.2 bar here. Okay, we need to calculate this difference. But we also need to provide a confidence interval to that by using the T quantiles and the standard error that we get from the difference, okay, the standard error for L1 minus L2. And it is obtained by what? square root of the variance, sample variance across replications under the first Q discipline divided by the number of replications under the first Q discipline plus the sample variance obtained across replications under the second Q discipline divided by the number of replications that we have performed for the second Q discipline. And then we take the square root of it to calculate the standard error. Then we multiply it with the T quantile here. Now, this value is available as 0.0102 from our table, as you can see. And the sample variance across replications under the second Q discipline is also available here. So in this formulation, that value, and the number of replications are equal and they are 8 are available. And sample averages across replications are also available. All we need to identify is the T quantile, my friends. The question asks us to build a T confidence interval with 95% confidence level. So we definitely need to use a 0.025 tail probability because the confidence interval here is going to be symmetric. And the question here is this: how do we calculate these degrees of freedom? Okay, so we need to find the degrees of freedom. Now, in the independent sampling procedure, most statistics books tell us that we need to use a degrees of freedom parameter here, which is 2 less than the total number of replications that we have used. Now, in the first Q discipline and in the second Q discipline, we have used 8 replications, which means in the whole comparison, we use a total number of 16 replications. And we subtract 2 from that to get the degrees of freedom. But this is the suggestion of many statistics textbooks. However, the true degrees of freedom is calculated for independent sampling, two sample t-test under independent sampling. The degrees of freedom parameter is actually calculated with a much more complex closed form formula, which is obtained here. I'm not going to explain the details of this formulation here, my friends. I mean, you are definitely capable of performing every operation within this formulation. Once this formulation is calculated, you need to choose the closest integer. Okay, you do not round it up or you do not round it to the floor. Okay, you choose the closest integer to that value. And the closest integer to the interior calculation is 14, my friends, which is consistent with the recommendation of statistics books in this case. However, there are some exceptional cases where the recommendation of the textbooks yield a different result than this theoretical formulation that calculates the degrees of freedom parameter. Now, the interior is 13.77. The closest integer to that is 14. Therefore, we definitely need to use 14 as the degrees of freedom parameter here for a 0.025 tail probability, 0.025 tail probability, and degrees of freedom 14. As you can see, the T quantile that we should get is 2.145. Now, we plug in 2.145 here, and we calculate our confidence interval. The confidence interval for the difference between the expected number of clients in the system is between minus 0.179 and 0.0243. Now, this confidence interval, my friends, unfortunately contains 0 in it. Therefore, we should say that there is a certain probability that alternative Q discipline policies applied, they do not affect the result in the expected number of clients in the system. Okay, so the result is inconclusive. We can never say the first one is better than the second one or the second one is better than first one in comparison of the system designs. At a 95% confidence level, the comparison is inconclusive, and we cannot say one of the Q discipline yields a less expected number of clients in the system than the other one. Okay, what we can do is to increase the number of replications, my friends. Okay, now for part B, it says if we want to reduce the half-width of the confidence interval found in part A to 0.03, how many more replications do we need in each simulation? Okay, so at this point, the confidence interval has a certain half-width. Let's calculate it with calculator. Okay, so what is my half-width? 0.0243 plus 0.179. So my half-width is half of this. My half-width is approximately 0.1. But the question is asking me to reduce the half-width to 0.03. And in order to do that, we need to increase the number of replications in both simulating Q disciplines, and how many more replications that I need to perform. This part is left as an exercise to you, my friends. All you need to do is what? You need to combine your knowledge from the previous example that we have solved by using the sample standard deviation. Okay, the sample standard deviation. I mean, all you need to do is this. This is the half-width, right? This half-width, and here M1 and M2 is equal to each other. So you can replace M1 and M2 with simply M, okay? You need to make this half-width less than or equal to 0.03, okay? All you need to do is, because there's a common denominator here as M1 and M2, okay? There's a common denominator. All you need to do is to keep that M value, this common denominator, in one part of the inequality and everything else in the other part of the inequality. Then you are going to replace that value with the Z quantile, okay, which is 1.96 in this case, if you check, okay. So for 0.975 cumulative probability, the Z quantile is 1.96. Or you need to replace that T value with that, and from that you need to find the minimal M value, okay? The minimal M value that you are going to get, okay? So it is not very hard. It is definitely not very hard because we have common denominators here. I mean, in fact, we can easily perform this if you like. Let's try to do that then, okay? So we say that. So I'm just going to do it here. So let's use a thick pencil here. So I say I'm going to use a Z quantile with 0.975 cumulative probability here, okay? And I have a common denominator M1 here, which I can simply put here as a common square root M, okay? And in the denominator, we are going to have summation of S1 square plus S2 square, okay? This should definitely be less than or equal to 0.03 in the context of the second part, which is left as an exercise to you, okay? Now, in that inequality, I'm just going to collect M from one side to the one side of inequality and everything else to the other side. So I say I need to calculate the Z quantile at 0.975% cumulative 0.975 cumulative probability, and we have S1 square plus S2 square here, divided by 0.03, which is the desired half-width for this confidence interval. But we also need to take the square of it because when M is collected on the right-hand side, we square it here. Now, the number of replications that we require is definitely going to be greater than or equal to this value, which is 1.96, as the Z quantile is collected from the standard normal table, times the square root of the sum of the variances. So let's calculate the sum of the variances here, 0.0102. So I'm just going to open my calculator again. 0.0102 plus 0.0079, and it is 0.0181. 0.0181 divided by 0.03. Okay. Now let's calculate that value again with calculator. 1.96. By the way, I forgot to square it. 1.96 times the square root of, okay, the square root of 0. Sorry, let's start from scratch. Okay, I am not very familiar with using this calculator. I usually use the programming languages. Let's calculate 0.0181 and calculate the square root of it. Okay, this is the square root. Now we multiply that value with 1.96. Divide that value to 0.03. Okay, then we calculate the square of this value. It is 77.26 approximately. Okay, 77.26. Now m should be greater than or equal to this value. The smallest integer that is greater than or equal to this is 78. So this means we have already performed 8 replications. In order to get such a confidence level for the half-width, in order to get such an accuracy for the half-width, we definitely need to perform 80 more replications. I'm sorry, 70 more replications for each Q discipline. Okay, not just 35 split to each other. We need to perform 70 more replications under each Q discipline in order to get such a half-width in this example, my friends. Okay, now you see the previous half-width was simply 0.1. I just want to reduce it by 70% to 0.03, but that makes me increase my number of replications from 8 to 10 times larger, approximately from 8 to approximately 80. Okay, so by performing 10 times more replications, you can only reduce your half-width to 0.03, my friends. Okay, so increasing the number of replications just to get an accurate result is a brute force approach in the context of simulation procedures, my friends. Now let's focus on part C, which is again an essential part. It says that it is then told by the analyst that the random number streams used in the replication is also used in the corresponding replication regarding to the other Q discipline. Now in the question here, it says we have used independent sampling, but there is a correction here in part C. It says that the random number streams that we have used in the first replication under first Q discipline is the same as the random number streams that we have used in the first replication of the second Q discipline simulation. That means we are using the common random numbers technique. Okay, it is not explicitly told by the question, but that means we are using the common random numbers technique, which means there is a further methodology that we can reduce the half-width of the confidence interval of the difference by using the common random numbers technique here. Okay, so we assume a correlated sampling. Correlated sampling means we use the common random numbers technique. Okay, I am very sorry, by the way, this question is explicitly stating that they are using the common random numbers technique in the sentence. I am very sorry for that, but it shouldn't have, I mean, or it may not have expressed it, but the first sentence already gives away the fact that they are using the common random numbers technique. Now the question is asking us, use this information. If you assume that the common random numbers technique is used, you need to answer part A again. Again, you need to build a 95% confidence interval for the difference between L1 and L2. Now here, the color of the situation totally changes, my friends. Now, instead of using the sample mean and the sample variance obtained across replications under each Q discipline, instead, we subtract the estimate that we collect from the second Q discipline's first replication from the estimate that we collect from the first replication of the first Q discipline. Okay, so 9.94 minus 10.12, because we have used the common random numbers here we are just going to eliminate the variance caused across replication estimations. Now, we definitely get much more solid results if we compare the simulation results, not using the across replication averages, but we can simply compare each replication with each other because they are using the same kind of input, which means if the random number streams are the same type of input values are going to be applied in the same replication for each Q discipline. The same scenario will be created in each replication under the same scenario, same input values. Imagine this is a banking system. This means the inter-arrival times of the clients are going to be the same in the first replication under each Q discipline, and the service times are also going to be same for each client, for each Q discipline simulation. This means while the input scenarios are the same, the uncontrollable input scenarios are the same for the two simulation design alternatives, we check the output. So it is much fair to compare the replications with itself and calculate a bottom row here, which is the difference of the first row and the second row. We simply subtract the second row from the first row to calculate the difference. And all we need to do at this point to check whether the average difference is less than 0 or greater than 0. If the average difference is less than 0, then the expected number of clients in this first Q discipline is going to be less than the second one. If the average difference's expectation is greater than 0, then we say that we choose the second Q discipline because it is much more favorable. So at this point, because we are using the common random numbers technique, we are going to build a confidence interval, not for the difference of the L1 and L2, but for the expectation of the difference here by using only the last row, okay? The first two rows are not important for us anymore. So we are going to build whether the true average difference can be 0 or not by building a confidence for this D values using these 8 observations, okay? The average difference across replications is minus 0.0775, which is here, as you can see. And the sample variance is 0.075. The sample variance of these 8 values, my friends, is 0.075. In fact, I can show that that is true. Okay, so let's say so let me scan these values. So D is a vector here. I am very sorry for that. Again, I need to start because I have made a syntactic error. Okay, D is a vector here, and I can calculate the variance, sample variance of this D vector here as 0.0079 approximately. And here it is a little bit different. There is a certain error because most probably I have made this calculation. I have made this calculation by rounding numbers, okay? But that error is not very important for us. Now, the sample standard deviation is the square root of this, and the sample standard deviation is calculated by calculating the square root of the sample variance of the differences. We divide it to, again, the square root of 8, which is the number of replications. And using the T quantile, again, obtained with 7 degrees of freedom and 0.025 tail probability, we build our confidence interval for the expected difference in the number of clients in the system, which is totally, this confidence interval is totally on the negative part of the real numbers line, which means for a 95% confidence level, my friends, the difference in the expected number of clients under this first and the second Q disciplines is going to be negative, which results in favor of the first Q discipline, obviously, okay? Okay, the first Q discipline seems to be better than the second one. Now, you see, if these simulation results are obtained with the common random number technique, if the question tells you that fact, I mean, if it tells you that they are definitely created under common random numbers technique, building a confidence interval by the assumption of an independent sampling will give you an inconclusive result. However, the common random numbers technique will tell you that the first Q discipline is better, even by performing only 8 replications, okay? So if the question indicates the common random numbers, it implies that the common random numbers technique is used, you should definitely use this approach to calculate the confidence interval for the expected difference in the number of clients in the system. You should be very careful about this, especially when you are solving your homework or if you end up with such a question during the exam. Okay, so that's it for today. And by the way, you can simply repeat part B for also part C. So let's just say, even if this confidence interval gives us a solid result that the first Q discipline should be favored with respect to the second one, some users may require a narrower confidence interval because you see the upper bound is very close to 0, right? The upper bound is very, very close to 0. So some users may say that I want to get even narrower confidence interval here by reducing the half width. What can I do for that? At that point, you should say that you need to increase the number of replications such that this half width is going to be less than or equal to a certain value. So right now, let's check. Right now, 0.1498 minus 0.0052. Your confidence interval's length is this, and half of it, 0.1446 divided by 2, the half of it is approximately 0.07. If the user tells you that I want to get a half width which is less than or equal to 0.01, then you need to make this half width less than or equal to 0.01, and everything, I mean, you need to take m to one side of the inequality and everything else to the other side of the inequality, and you need to replace that t quantile with the z quantile again to identify the necessary number of replications that you need to perform for a desired accuracy of the half width. Okay, and you can practice this later at home, okay, which can also be another question in the final exam. And by the way, in the second question, we almost have a similar situation as the first one, okay? So the second question here, it basically tests whether which scheduling policy is better than the other one. Again, in the first part, it assumes that they have performed independent sampling, but in part C, it assumes that they have used the common random numbers technique, and it asks to perform part B again. In this second example, okay, again, you can determine how many more replications that you need to perform. But this time for part B, there is an explicit solution. And also for part C, again, it ends up determining the number of necessary replications to reduce the half width of the confidence interval to a certain value, my friends, okay, which is 0.1 in this case. So you can study the second question to understand what we have done for this last question today. But this is left to you as a practice. So I'm just going to stop recording at this point.